Welcome back to the channel. My name is Jan and this is another episode of the Minuteman project. And I think this is going to be a very special episode because I think we're at the point that we can finally see where the true limits of stepper motor systems are. So let's have a look. This is what we started out with. It's a NEMA 17 with a 25mm effective diameter pulley on it. This is a NEMA 23 style servo in this case because the stepper motors are put on the machine with a 40mm pulley. And what we found out in the latest episode is that those weren't really scaling with the current I put on there. The reachable amount of acceleration wasn't going up linearly when I increased the current. So today we're doing the natural thing, and as loads of people suggested in the comments, we're putting on bigger diameter pulleys. This is a 100mm pulley, and on the machine I already have the 120mm and the 80mm version on here. We're going to run some tests with all of these, have this one as an intermediate step to put on there. And then, right now, we're running the OMC steppers. It's upside down, but you can see if this is of any interest of you. 3 Newton meters, 4.2 amps, NEMA 23 style steppers. Today, we're also having a look at a different motor. This is something a company from Munich sent me. It is also a NEMA 23 stepper motor that can also handle 4.2 amps and also has around 3 Newton meters of holding torque. We're gonna have a closer look what makes this so special and gonna throw it on the machine and see if this enables us to reach our limits. So I guess it's time to play the intro tape and then get straight into testing maximum accelerations on all these different setups. So let's go. Alright, we're on the Minuteman machine and we're gonna do some testing now. Essentially what we're trying to find out is the maximum reachable acceleration per given current on the coils. This is just doing a straight line movement back and forth like 5 times at 1500 millimeters per second printing speed, and with each step it's going to increase the acceleration by 10k. I think the maximum I've up in here is 600k, and let's hope we have to dial that up today. I set up this crude looking table here and we're going to fill in some blanks. See, this is like the 80mm pulley, and I think 4 amps per motor is what my current supply is capable to do. Let's start with the 120mm, I guess, and test's gonna look like this. Hit cycle start. 10k, 20k, 30k. This is 1 amp per phase. And as you can see, it did the 100k, so I have to go to the next step file. I'm gonna conduct these tests because there will be loads of missed steps, etc., and me setting up everything again. Let's get back to the graphs, and maybe I put in some of the highest values movements I can achieve. So see you again in a minute. So the last one was 400k acceleration, 2 amps, 80mm pulley. So we got some first results in. So these are the values I could find. These are the corresponding amperages, and these are the maximum accelerations. As you can see here, that's quite interesting. The 80mm is on top, and you can see in both versions that it is somewhat climbing linearly to a certain point. With the 80mm pulley, that's around 2 amps, and with the 120mm, it's somewhere to 1.5 amps. I can reach accelerations of like 300k, or in this case 470k. Then from this point on, it's just slightly dropping off. So this is kind of the same as the results I got the last time when we ran the initial 40mm pulleys. We got the maximum acceleration at like 1 amp, and from this point on it was just getting wilder in terms of stress put into the system, but it actually didn't increase our maximum acceleration. That took me way longer than I thought it would, but yeah, I got some results for the 100mm diameter pulley. There's so many little things to dial in before I can actually do testing with proper results. In this particular case, I realized that this motor is bad. If I would care to know, I would slice this open and see what the problem is. Maybe it has got something to do with the load on these bearings. Maybe these guys aren't really designed to do this kind of task without having a proper secondary bearing up here. But whatever, I couldn't run the tests with the motor I anticipated it to. So I had to switch these up, and that took a lot of rewiring, etc. The yellow line is everything I was able to produce in the last 2 hours. As you can see, it's in the beginning, let's say to 1.5 or maybe to 2 amps. Let's say it's within reason with my measuring capabilities here. So take everything you see here with a grain of salt, at least plus minus 10% to all the results, because there are so many variables in here. I try to keep everything else consistent in terms of microstepping and cable length, rotation diameter, etc. It's no else parameter is changed except for the amperage. And as you can see, up to this point, it's pretty much on par, and then it settles in and also tapers off a bit at the end, like we see with all the other pulley sizes. So our sweet spot seems to be somewhere in the neighborhood of 1.5 amps of current. The 80mm diameter gave us the best results. That's kind of interesting. I wasn't really expecting that when I did some simulations on here. But for now, I think it's time to have a look at a different motor, because these OMCs were great for like first testing purposes. They were really easy to obtain. I had just 2 days of delivery time. They were dirt cheap. These were 25 euros a piece. And it got me started in finding out if NEMA 23 is the right form factor for this machine. At the end of the last video, I also gave a shout out to anyone knowing some kind of a company or technology using stepper motors that would help us to reach our goals. And a guy named Andre called me up and said he is working on a quite similar project. And I think you will see that in some future episodes, I guess. We're not clear on the details, but he gave me a name of a company here in Munich, which is called Nanotec. I wrote them an email and asked for, you want to do a collaboration on this project? They sent me some top-of-the-line stepper motors. We had a quick call about what they expect the results to be. They won't guarantee any value or something, but they were pretty interested in finding out how they compare to the OMC stepper. Let's put some values together and see you in a minute. So I got the 2 motors lined up on the bench here, and let's just compare 3 little key facts. So those are both rated at around 3 Newton meters of holding torque, and they each can handle 4.2 amps of rated current. The rotor inertias are lower on the OMC one, which is usually the better thing for us, because it would allow us to gain more acceleration with less torque. That's 340 grams. The Nanotec is at around 480 grams. So without going into any further details on the spec sheets, this is their top-of-the-line stepper motor with FluxFocus technology. And what I can give you, like somewhere in the video description, there will be a link to the website where you can get all the additional details about this. It basically boils down to this is a very efficient stepper. They do have, as my understanding of it is, additional permanent magnets sitting on the teeth of the stator, and therefore allows them to get the maximum out of every amp of current they throw at it. That makes them really efficient in terms of torque. So these are the torque curves in relation to the speed. You can see the blue line is at 24 volts and this is at 84 volts. So basically you have to extrapolate a bit to get up to like 57 volts, which I'm running them at right now. With the pulley size of 80 millimeters at 1500 millimeters per second printing speed, it's right about this 325 RPM we're using them at. Yeah, and judging by their document, this stepper should have full torque available at our rated speed. We'll see what all this black magic in here does in terms of reachable accelerations. Let me slap all four of them on the machine. Then we have one axis with a 80 millimeter pulley and one with the 100 millimeter pulley. Let's see if those numbers add up with the OMC steppers, and then we'll make a decision what kind of the final pulley diameter will be, and let's do a test run afterwards and see how that translates into benchy times. Let's go. I got the Nanotec motors installed, 80 millimeter, 100 millimeter diameter pulley. One thing I forgot to mention, I mean it was pretty obvious, but I didn't mention it. Those motors, even though they're rated kind of the same, is considerably smaller. This is a 76 millimeter length. The OMCs are about 110 mil in length. Also, they are equipped with it's a single shaft sticking out at both ends, because usually this is equipped with an encoder. This is used in closed loop applications usually. Alright, so let's run the same tests. I'll put a snippet of somewhere in the middle in this, and then we'll see again at the results. So this is with the Nanotec motors running at 2.5 amps right now on the y-axis with the 80 millimeter pulley, and this is the sweep from 400 to 500k accelerations. Okay, let's just continue. 500k start. 520k it did successfully. Alright, we're back at my screen. So here are the results without further ado. As you can see, the red line represents the 80 millimeter, the yellow line, the 100 millimeter pulley. And this is a bit different than what we had before. Because, yeah, you can see that it isn't flattening out and then decreasing. In the case of the 80 millimeter pulley, it is still able to increase its performance with added current. With the 100 millimeter pulley, it is doing the exact same behavior. It has been a pretty long day. So I've been here for 8 hours fiddling around with this machine, and I'm pretty tired for today. So I think I'm just going to leave it as is. get the CAD work done for the 60mm version, put it on the printer, and yeah, see when I get next time slot available for working here. Different day, same topic. So follow me to the machine. So what you can see here is I have upgraded the x-axis in this case to the bespoken 60mm diameter pulley. And I've been conducting some tests, and those were pretty interesting. So again, 2024 screen share. You can see the green line up here is climbing and climbing and climbing, and it got to 3.5 amps. And I ran these tests 3 times, and it was just shy of 900k acceleration values. Also, these tests turned out to be pretty consistent. I did all of them 3 times and it was pretty much spot on. So you think, hey, why don't you keep on doing? The thing is, I can't even reproduce the 3.5 amps. So and that's quite interesting because it's either, the motors are quite hot right now, so I have to cool them down for a minute. See if that changes them back in their performance, or if it's something else. So I've been keeping all the other parameters the same throughout the whole test, as I said before. Let me start differently. If I install a new set of pulleys, etc., I do enable these stepper motors to find their natural position where they like to sit in, so between 2 full steps. And then I set this on my center, tightening these ropes, so in its natural stepper position, these will be slack free. I'm securing them with these screws. Accelerating up to 900k, I noticed that the slack is growing, so that means there are 2 options. It's either this tension system is slipping or it's slipping up here on the screw. Nevertheless, I do have a little bit of play in this system, and that was helping with possible accelerations big time. In order to reproduce this, I kept going back and forth with loosening and tightening all of these, and I can't really seem to find a very good sweet spot. But as I said before, I've ran this multiple times, and I know I'm not fooling myself with these values, so it is possible. I just have to find a way to do it reliably. So also, what you're gonna see with these steppers, it's the completely different thing to the OMC ones or even the LDOs I had before. So with a bigger size pulley, the performance did decrease. And also what I found out that this point of saturation, where more amps doesn't translate to more acceleration, is becoming sooner and sooner. That's a behavior I can't really find in here. So also there is a bit of a saturation, but it still keeps on climbing just a tiny bit. And the lower I go on the pulley size, the more climbing it does linearly. So I do have somewhere in my pile of pulley diameters, this is just third of it. I do have the old 40mm pulleys, which I'm going to put on the y-axis now and see where our limits are. And again, it's a few hours later. I rebuilt this again with the older 40mm pulleys, and I'm at the point where it starts to get really interesting. So I've been doing these measurements again just for a straight single axis move, and these are on par with the 60mm pulley. And then I did the next test, and at 2 amps it was somewhere in the neighborhood of 480, which was as expected with the 60mm. But then I changed the tension settings just a slight bit, and I still got it on the same settings. So I'm gonna set the camera up here. What I do with these tests is just put my 2 fingers up here to simulate the effect of the air bearing that will be installed later on. Otherwise it will be tip in too much and interfere with my results. And now we're running 400 to 500k on this axis. Starting now. That was 500k the last. Now we're starting from 510k. Go. Let's go on. I haven't done this myself. So this is y-axis starting at 610k. Okay. So just to prove to you that I'm not shitting, this is being set by the G-code. It actually did 630, well, the 620k was successful at just 2 amps. So let me put that in here and let's continue. I think what goes to show here, that this system's capabilities are way up here. It takes some time to figure out all the nitty-gritty details on what I gotta do. And to be truly honest, I have no idea if I rerun these tests now where I do end up. So the slightest variables in this case, cable tension, make all the difference. So I have to find a way either to measure that in terms of frequency or have a force sensor or something like that in the line. With the open loop steppers, I have very limited resources in terms of data from the motor itself. So let me check. Literally 2 minutes later, when you just thought you had found the real sweet spot. So, these measurements are driving me nuts. And part of it is because it is not reliable or, let's say, repeatable in its results. I've been fiddling around, as I said in the last clip, with belt tension or cable tension. I can reach really high values, but I can't reproduce them reliably. And that is a problem because there are so many things on this machine that have to line up in a later attempt to actually 3D print something. We end up in a situation where just 1 of 100 attempts will be successful, and that is not a reliable base I want to have. I tried to get a few variables out of the system, and that is by using these parts. What I'm trying to do here is get valuable data from one of these motors only. And we're going to do that by simulating the weight of this moving bed here in the middle. We're in the situation that because we're using cables instead of something that is properly rigid in both direction, push and pull, if we move along this axis, only one motor is active and it has to do all the acceleration, so it's pretty easy to calculate the momentum it puts on the motor. So what we're doing now is conduct at least 4 tests. I figured that with these motors, these are way ahead of the OMC steppers, so we're going to stick with them for now. Also, I've concluded that with bigger size pulleys, that doesn't help these motors. So I'm somewhere in the neighborhood of 40 to 60 millimeter diameter pulley, which works best with these motors. That's where I get the best results. So we're gonna stick to those. What we do now, this is like a blank pulley, just like the others with just these 2 lips at it. And we're gonna stick it on here. And what we're trying to find out is what if this motor would run without any additional weight on it, what is the absolute limit this motor can do in terms of accelerations? That will tell us where are the true limits if we shave off gram after gram from this moving build plate. And it would be our main priority to get this as close as possible to non-existent. Next thing we're going to do is we're going to add rotational mass. And these are carefully calculated to match whatever we got in the middle as of right now. This is 70 grams. And this piece I can glue in here later on will simulate what the inertia of this is in linear movement and have it in here as rotational inertia. What my hopes are to conclude from this test is how much of potential acceleration is being lost because of strings. Everything from cable tension to harmonics to frequencies to whatever will be put out of the system. So it will tell us what, with this weight attached, the maximum acceleration is without having these ropes on here. And we're going to do the exact same thing with the 60mm pulley. Going to put that on here, measure it without any additional mass attached to it, and then we're going to put on this plug and then see what we can conclude from these results. For the diameter pulley with rotor inertia attached at 1 amp. The first set of tests is done. As you can see, this is for the Nanotec diameter 40 pulley. And you can see red one is just the pulley, yellow one is simulated weight, and this is the previous data set from when I was doing the tests with the build plate attached. This yields some pretty interesting as well as integer results. So as you can see, the red line represents what this motor standalone is capable to do. So with this diameter pulley, we will never exceed 1.35 million millimeters per second squared acceleration. This tops out no matter how much amps I'm gonna throw at it. Then you can see the yellow line represents what the influence of the added weight from the build plate actually is. So just by moving these 70 grams on top of just the pulley, we lose this amount of possible acceleration, and this tops out at around 870 K. So with this current iteration, this will be our limit. We can't exceed this. And as you can see with the blue line, I think that's pretty interesting because at a few points we almost match that. Right at this point, the influence of our cable was basically non-existent, as well as maybe here, and it's slowly approaching to this point. So the yellow line is what's possible with this weight, and everything between these two lines is what our system with the cables and tension is basically what we're losing. So let me conduct the tests with the 60mm pulley and then draw a conclusion. So I took the different motor because it's cold and they got the same conditions, and this is the 60mm pulley at 3 amps. And I think it failed in 1.85 million millimeters per second squared acceleration. Alright, let's talk about the results here. So the 40mm one you saw early on, and we discussed that already. This is for the 60mm pulley, and as you can see and as expected, the red line with just the pulley is way up higher, because that makes total sense. The weight of the pulley itself doesn't really change that much, it's just a few grams of difference, but it has to move way less. So with just the pulley attached to the motor, we can run up to 1900 meters per second squared. With the rotor inertia attached, we are in a similar neighborhood to the 40 millimeters, maybe 10% higher than that in average. But also the blue line, which is like the actual measurements I did with everything attached, has a way higher gap between what's possible and what was possible in reality. And therefore, I think for now, I'm going to conclude to go with the 40mm pulleys, because either way, we need to increase it way more to eventually go down to a 1-minute benchy, and it will not be possible with both of these. But this seems to be a bit more of a reliable setup. If I go on and ran these at about 2 amps or somewhere in the neighborhood, that will help tremendously with testing and have a reliable base, because with 2 amps on the motors I can pretty much run them all day and don't get into any cooling issues, and also have, in a best case scenario, well over 600k of possible acceleration, which is still a freaking lot. I'm having the feeling that this is going to be a long video again, but I just want to take this very moment to address something about engineering itself. We're doing a lot of base work to get data and derive actions from that. There is this old saying of, if you got an hour to chop down a tree, you better spend 50 minutes sharpening your axe. And that's exactly what we're doing here. So we could go into just printing stuff, shaving down seconds after seconds, but it was very clear early on that this wasn't going to be an easy task, and we have to do smart decisions about our time, otherwise we'll be wasting it. You could argue that by doing all this experiments with slinging the bed around with the cables attached, before doing actually the simulating part with the rotor inertia, could be kind of a wasted time. But now I got all these data points available to me, and now we can derive a decision from there. In terms of possible benchy times, let's say we take our highest value we reached today with the rotor inertia attached, and that is roughly 1 million millimeters per second squared. Then this is still not far away, but there's still something to do before we can get a sub 1 minute benchy according to the speed benchy rules, which is open steppers. To shave down a benchy time in half, you basically have to quadruple the acceleration in the system, considering everything is linear in that regard. So I think to my most recent calculations, we need about somewhere in the neighborhood of 2 to 2.5 million millimeters per second squared acceleration to achieve that. And I think it is very clear to say from this point that with these kind of systems, it's almost impossible. I did say almost, but let's have a look at what we got here. So these are top-of-the-line steppers from a German manufacturer. Those are run with absolutely top-of-the-line stepper drivers, which are supplied with the maximum voltage that is somehow possible on the fastest processor that is out there for 3D printing applications. And even if we do add input shaping, which totally isn't a thing up to now, I don't think we're going to reach those values. But that's not a problem. I mean, essentially what we're trying to do here is answer the question, and if it's no, well, then that's okay. So I think there are more and more indicators on that it is not possible with off-the-shelf components. Yeah, so I think what we do now, I want to wrap this up with finishing for the time being, putting, I think it's going to be the 40mm pulleys on here, have everything in kind of a, for now, final situation, and get a reliable moving platform on this machine. And then build the proper hot end that is able to keep up with the current state of it. I think it's time to have a sneak peek at what's about to come. Let me line that up for a second. So as I said, these steppers were provided by Nanotec free of charge. I didn't get any extra money for presenting them here. It is not a real review or something like that. I'm just going to use them on these machines to achieve our goals. That's kind of the same thing with the hot end situation. So in the last couple of weeks, I reached out to Bondtech, which is located in Europe, in Sweden, and had a really nice chat with the engineers over there. And they provided me with some top-of-the-line materials to build a really proper hot end. So this is the Bondtech LGX Pro, and I'm going to combine that with some pieces of slice engineering. This is their copperhead heatsink as well as the copperhead heat break. Yeah, and since breaking records isn't that easy, this might help. So you can basically see where I'm going with the hot end situation. I do have my CAD plans almost done, and I think next video will be about building and running this hot end, and let's see if we can reach matching numbers to our current motion system. And yeah, for this video I want to thank Nanotec again for providing these motors. I will put a link somewhere down in the description, and you can see throughout the video what this actually enabled us to do. So these are running way faster than the OMC ones, which according to the spec sheet should deliver the same performance. They stay considerably cooler and do have like half of their weight. So I have no idea how they do that. Maybe we can go into this in a future episode, but for right now, I'm gonna build this in a representable state again, and then maybe let's see if we can run a dry run of a Benchy somewhere in the 2-minute neighborhood. So yeah, let me see if I can do that, and we'll meet again soon. Alright, probably the last try for this evening, attempting a 1-minute 57 dry run of a complete Benchy. I don't have a stopwatch here, but you can see it on the slicer, I guess. So here goes nothing. So it's really late in the evening and I just finished another session here at the Minuteman machine. I want to go home, I want to edit this video to get it online, and so much has changed on the machine, so let's have a look together. So we're going into detail in another episode because this is extremely long again as a video, but just to get an overview, I drilled this hole and that hole and that hole in here to gain access to already the central hole, which is putting shop air right in the middle of this. I could then rearrange these motors. As you can see, they're now not in a symmetrical orientation anymore. They're more like 30 degrees to the middle axis. And yeah, the main thing you can see is this really crude setup for right now. As I said, shop air is coming through the granite table and is being distributed in this air bearing. Those 8 pads are being pressurized by the shop air, and then we got a very small but defined gap. Can't even really show you that with this camera setup. So basically, in its current state, it is almost locked. But as soon as shop air is applied, there is a very fine gap to the bottom and top surface, which is this glass plate for right now. I do have proper glass plates lying here, but I lack of a water jet and have to get that out to a different company. Yeah, just want to do that when I got the final measurements of everything. In terms of performance, this added a whole lot. You saw me in the test putting my fingers on there to basically lock these tipping degrees of freedom from it, and this setup is like preventing that entirely. From the moment I put this on, all the measurements became somewhat like reliable again. This is running pretty darn good, except for these tensioner things, which like were breaking in all the previous attempts. I've done 4 this evening and I had 4 of these break. The fastest would have been a 1:50 dry run. This dry run turns out to be a 2:06, which goes to show that I can't really give anything on the slicer estimates. I wanted to be right on the 1:57 by Monica McWolf and actually tie that. I mean, it's not a 3D print. Those are 2 pair of shoes, but yeah, just out of respect for her and all the help she's been giving me throughout the whole project, I think that would have been a cool thing to do, but that didn't work out. So also to give you some numbers, this was ran at 1500 millimeters printing speed and 450k acceleration throughout the whole print with a square corner velocity of 20 millimeters per second. And still, there is no input shaping on this machine. I think that's one of the next things I'm gonna tackle, yeah, to get this a lot less wild in its movement. Yeah, apart from that, I already shown you the pictures of what I got for the hot end in the schedule. So I think these will be the next things you're gonna see here on this channel. As an update, I'm going to close this up for this video. Feel free to leave a comment with any suggestions or whatever came to your mind. Join my Discord. There's a link down in the video description. And yeah, see you guys next time. Bye.